Have you ever looked at a giant skyscraper or a super complex airport and just thought, how? How on earth do they even begin to build something like that? Well, today we're going to pull back the curtain on the digital revolution that's completely changing how we build, moving us way beyond old school paper blueprints into the world of smart, living 3D models. And seriously, think about that question. You've got thousands of parts, dozens of different teams, millions of dollars all on the line. The old way of doing things just doesn't work anymore. One tiny mistake on a piece of paper can snowball into a massive, eye-wateringly expensive problem out on the job site. So how do we stop that from happening? The answer is a totally different way of thinking. You see, the old way was all about thousands of separate 2D drawings. It was like trying to navigate a whole city using a giant, messy stack of paper maps. The new way, which we call BIM, brings it all together into a single, smart 3D model. Just imagine having a living, breathing digital globe of your entire project, where every single piece knows where it belongs. Okay, let's dive into this, because the real magic of BIM, and that stands for Building Information Modeling, isn't just the 3D part. It's the I, the information. That's the secret sauce that turns a pretty picture into an incredibly powerful tool. So in a classic 2D drawing, what you'd call a CAD file, a wall is just, well, it's a bunch of lines. The computer knows it's a rectangle, sure, but it has zero idea that it's supposed to be a wall. It has no real-world smarts at all. Now, moving to 3D is a step up. You take those lines and you make them a three-dimensional shape. We can see its height, its length, its width. It looks like a wall, which is awesome for visualizing things, but it's still kind of dumb. It doesn't actually know anything. And this is where everything changes. In BIM, that 3D wall becomes a smart object. It's basically a container for data. It knows what it's made of, what its fire rating is, exactly how much it costs, who the manufacturer is, everything. It's not just a shape anymore, it's a living piece of a project-wide database. And once you have a model where every single object is packed with information like that, you can start asking it some really sophisticated questions. This is where we start to go beyond just the 3 dimensions we can see. This shows the progression perfectly. 3D is the what, the physical thing. Then you add 4D, which is the when. You link every single object to the construction schedule. You can literally press play and watch a time-lapse of the entire building assembling itself digitally. And then comes 5D, which is the how much. You attach cost data to everything, so you're tracking the budget in real time as the design changes. Now, all this power creates a new kind of problem. I mean, if every single nut, bolt, and light switch has tons of detail from the very first day, the model would be impossibly huge and slow. So how do you make sure the right people get the right amount of information at exactly the right time? Well, the solution is this incredibly smart system called LOD, which stands for Level of Development. It's basically a framework for managing all that complexity by saying exactly how much detail a model element should have at each stage of the project. You can think of LOD as a universal language. It makes sure that the architect, the engineer, and the contractor are all on the same page. Everyone has the same expectation for what done means at every phase. No more confusion, no more guessing. And what's really cool is how simple it is at its core. LOD is just made of 2 parts. The level of geometry, or logi, that's how it looks, the visual detail, and the level of information, or lo, that's what it knows, all that juicy, non-visual data that's attached to it. So let's see how this works in the real world. We're going to follow one single piece of an HVAC system, a duct, and watch as it climbs the LOD ladder, going from a vague idea all the way to a finished, installable part. This table gives us a great bird's eye view. The LOD scale usually goes from 100 up to 500. And as you climb that ladder, both the shape and the data get more and more precise. It's like slowly zooming in on that digital globe we talked about, going from seeing continents to seeing a specific house number. So way at the beginning, around LOD 100 or 200, our duct isn't much to look at. It's just a generic box. Its only job is to be a placeholder, to say, hey, we're going to need an HVAC system roughly this big in this general area. It's all about conceptual planning, just blocking out the big moves. Then you hit LOD 300 and things get serious. That generic box now becomes a specific, well-defined duct. It has exact dimensions, an exact location, and we know what kind of duct it is. This is the level where the different engineering teams can really start coordinating their work. Next up is LOD 350, which is a super critical step. This is where we make sure our duct plays nice with everyone else. We check it against the steel beams, the plumbing pipes, the electrical trays. The whole goal is to make sure it's fully coordinated and, most importantly, clash-free. And finally, at LOD 400, our digital duct is ready for the real world. The model now has every single detail needed for a manufacturer to actually build it. The exact lengths, the connection types, the insulation specs. It's basically a complete digital instruction manual for building the physical object. Okay, so we've got this super smart, data-packed model that grows in a structured, predictable way. So what? What's the actual real-world payoff? Why do we go through all this trouble? This quote just says it all. Every single problem you find and fix in the digital model is a problem you don't have to solve with expensive labor and wasted materials out in the field. It's all about building the project twice, first virtually, where it's cheap, and then once physically. And the single most powerful example of this, the absolute killer app, is a process called clash detection. Honestly, this one thing can justify the entire effort. Here's how it works. In the old world, an architect might draw a duct, and an engineer might draw a water pipe going through the exact same spot, and no one would have a clue until the installation crews showed up on site. That leads to delays, finger-pointing, and tons of money wasted. With BIM, the software automatically scans the model and finds that collision, the clash. It flags it for the designers so they can fix it with a few clicks, months before construction even starts. And the results? I mean, they're just staggering. We're not talking about little, tiny improvements here. We're seeing rework costs slashed by 75%, schedule delays cut in half, and the accuracy of what gets built goes through the roof. These are truly game-changing numbers for a massive industry. So this leaves us with a really exciting thought. By creating these digital twins of our buildings, we've learned how to solve problems before they even exist. So the big question is, what's next? What other impossible challenges can we solve with this power? How can we use these living models to design buildings that are more sustainable, more efficient, and more incredible than ever before? That's the future BIM is building, and the blueprint for it is getting smarter every single day.